All right, class 2. It's quarter after. I guess everybody who's going to be here is here. Last week we talked about safety. Probably you put those things somewhere. Basically, don't be afraid of electricity. Respect it. The stuff that's in that wall outlet right there will kill you dead if you mess with it incorrectly. The stuff that we're going to mess with, like we kind of did a little bit of math last week, theoretically, under a very perfect, idealized set of conditions, the 5 volts on your AVR microcontroller could kill you, but wow, you'd really have to try, right? You'd have to stab it into you and build the bridge across your heart, and maybe it could stop your heart. It's close. So last week, I talked about Kirchhoffs Laws and Thevenin, and I lied to you. Those were it is Kirchhoffs voltage law and Kirchhoffs current law. Norton and Thevenin's came up with ways to translate between different representations of the same circuit in the power supply domain to make life easier for analysis and whatever. So we're not going to talk about those, but we got to do some refreshers. So stay away from putting your tongue on anything worse than a 9-volt battery. So last time we learned some basics. E, and I called this wrong last week too. I said it was electromagnetic force. It's electromotive force. The unit are also known as voltage or tension in really old stuff. You don't see that anymore. And the unit is volts. And because it's voltage, sometimes you'll see it as V or E. So V. I is current. Unit is amperes or amps. Whoops. A-M-P-S. Letter A. I, because C is a capacitor. And little I generally means either AC or the square root of -1. Because everywhere else in the world you'll see I, square root of -1 is I, it's an imaginary number. In electrical engineering, it's J, because I. And what we do, like I was talking about last time, often we'll use a little I in AC circuits and things like that to differentiate between DC and AC. Not always, but sometimes. EI, let's see, V. V equals IR. R is another one of our basic elements, resistance. It's in ohms. And it is a Greek letter, omega, capital Omega. And then the last one is power. And power is in watts, big W. V, I use V, not E usually, is equal to I times R. P is equal to I times V. And I showed you the triangle last week. That's the easy V, I, R. V equals I times R. I equals to V divided by R. R equals V divided by I. Simple algebra on these things gets you where you need to be. If you do some solving, usually you find that P is equal to I squared R because IV times I is I squared R. These are probably the 3 most common relationships you'll use. So we talked about also in a circuit, this symbol is specifically a battery, with the long side being the positive side, what we would consider the positive side in conventional current flow. And current flows out of the battery this way and comes back into the battery this way. Current has to flow in a loop. Comes back, has to end where it started, if you want to think of it that way. Talked about the history of this thing. This symbol, this is the anode and the cathode on the battery. Anode's positive, cathode's a negative. Except in chemistry where anode is the negative and cathode is the positive, which always screwed me up in chemistry class. But most of your common materials that you'll use for batteries are about 1.5 volts for the galvanic junction. So you would see this would be a 1.5 volt battery, and that would be a 3 volt battery, 4.5 volt battery, a 6 volt battery, and so on. And you see some really old schematics with tubes that are having 500 volt circuits, and they kind of quit about there, and then they write a number on the side of it. Because you have to draw a lot of these things to get there. So what we often use is either this or this, which is an idealized voltage source. So last week I was telling some lies, and I'll continue to tell the lie for a little bit. But what you'll do is this plus minus is 5, if I put a 5 out here, that's a 5 volt source. There's also an idealized current source, and you'll say, I don't know, 5 amps. So, and that shows the direction that it's trying to push current. An ideal voltage source has 0 resistance. It is a short circuit as far as signals go. A idealized current source, infinite resistance. So you figure these out and what that means, practically speaking. I'll leave that to you if you're really bored. And we talked about an R. That is horrible. Let's try this again. An R resistance, this is an R, and it has some resistance in ohms, so 50 ohms is common. Okay? Questions at any time? Ask. If I get boring, feel free to go throw rocks at me and run fruit. That's fine too. All right. So I think we've hit the biggest part. So last week we talked about the most basic circuit in the world. So I'm going to draw a very simple schematic. A schematic is a representation of a circuit in a form that's easily understandable, relatively easily understandable, as opposed to actually drawing a circuit board and the way it actually looks. It'll look totally different. So this is the most basic circuit there is. Okay, this is signal ground. That's chassis ground. Usually, it depends. This is, actually that's chassis ground, that's earth ground. The mnemonic you remember is a ground, the whole world ground. All grounds on a power supply will eventually come back, and all branch circuits, they'll come back to a single point. Ground is number one in a building or a house. It's your safety. We make things so that if something inside the device, I've got 110 volts on the wall there coming out that'll kill me. If it should for some reason fault to the case, it'll immediately go to ground and short it out. It'll blow a breaker, and even if it doesn't blow a breaker, I've got a good chance that it's a whole lot less resistance than me, so it won't kill me. We carry grounds all over the place for just exactly that reason, to protect them. If you crack open your wall, you'll see a black wire. Black's your hot wire, I think, white's your neutral wire, and green is your ground. The truth is, ground and neutral are usually tied together back in the fuse box, but ground is the one that goes out to cases and protects you. It's a safety ground. In a circuit, that's our reference point. So we reference all of our measurements to that point. So if I say the voltage across here is 5 volts, that means with respect to this point, I am defining that as 0 volts. It's 0 volts. It may not really be 0 volts, but the difference in voltage between these 2 points is 5 volts in this case. Oh, we also talked about the schematic, the dot. The dot means that's where these 3 wires connect. Convention is you put a dot anywhere wires connect, and convention is you don't do that. because that means that wire crosses and doesn't actually connect, and sometimes that's hard to see. And so you can create confusion. So convention that not everybody follows, but convention is do this so that you know that these connect to this circuit and that one doesn't. In old, you don't see it so much anymore, but in old stuff you'll see this.
The loop, yeah.
It jumps over it. It's not connected. Okay, so again, I'm holding these classes at a really simplistic technology level. Most of the people who are going to be watching this or whatever who are here want to do it for maker reasons. You want to make blinky lights, make some motors, simple motors move, remote control cars, things like that. So I'm taking that bent on it. What I expect is we'll go through this, we'll go through special devices that are the most likely things to be used. And if there's questions, then we can talk about them. But I think where I'm going to head with this is microcontrollers like Arduinos and not a Pi, that's above a microcontroller, but it's an extension of. And we'll get into this box, this empty box that is a microcontroller that has a core with a bunch of peripherals around it. And what I think we'll end up doing is talking, each class we'll talk about this peripheral and how it works. And what are things you might do with it, how to use it, and maybe give a simple homework question. Here, you've got an Arduino, go make this work. Do something with this, and I'll come up with some idea. Go do this with it, because the way you learn is through doing, right? And that cements it into your mind. Oh, I did this. This is how that works. So eventually it'll be a skip, and we'll finally get to some of this stuff and the simpler ends of it. And I'm not great with code. I can write some and I can read some. I'm not my friend Charles I was talking about, but we can get places that get you simple stuff going and get you where you want to be. All right. You may have noticed I skip around a lot too. So in a simple circuit, we've got Kirchhoffs voltage law and his current law. And I'll repeat again, I have heard this occasionally pronounced Kirchhoff. So if you hear Kirchhoffs Law, it's interchangeable. So his voltage law says that the sum of all voltages in a loop must equal 0. So if I've got 5 volts, if I start at 0, I say minus 5 volts. I've got some voltage here. Because current is flowing this way, this side will be positive and this side will be negative. But you don't have to say it will be, you can just choose. So we'll say plus VR, because there's going to be some current flowing in the circuit. Remember, V equals IR. That looks like an H, I'm sorry, I. So minus 5 volts plus VR equals 0. So the sums of those voltages must equal 0. Practically, that means in this case, VR, simple algebra, equals 5 volts. Right? So add 5 volts to both sides. Because there's no other loads. A load is something that consumes current, turns current into heat, which is power. There's nothing else on here. If I were to put another resistor here, now we're going to start getting into some of the more interesting stuff. So today we're talking about series parallel. 2 resistors, R1, R2, VR2, plus minus VR1. So this is a series. Two resistors. That is a series circuit, R1, R2. Last time we talked a little bit about water flowing and a resistor sort of like a neck down in the pipe. Causes the water to slow down going through it and create pressure behind it. Think of or a longer pipe, if you will, because a longer pipe has more resistance to fluid flow. So the total resistance, RT, is equal to R1 plus R2. Simple, exactly what you would think it is. If I come back here, I come around, I start again at 0 volts, so I say minus 5 volts, whoops, plus VR1 plus VR2 equals to 0. And this is actually where this comes from. It's an application of Kirchhoffs voltage law. VR1 plus VR2 is equal to 5 volts. If I know, for instance, we'll say this is 5 amps. If I know that's 5 amps, I know that this is I, R1 plus I, R2 equals 5 volts. I can pull the I's out, so I, R1 plus R2 equals 5 volts. So that tells me R1 plus R2 is equal to 5 over 5 equals 1. R1 plus R2 is equal to 1 ohm. But right here is the proof that it's series. Don't want to kill you with math. I'm going to try and stay away from math. This is about as hard as the math gets. But this is important later. When you're making things, this is important. The next rule, and I won't, is a offshoot of Kirchhoffs current law. Kirchhoffs current law says that all of the currents entering and leaving a node must equal 0. So I have some current coming in here, and I have some current going here. That's supposed to be a 1. And that's a 2, I2. And here is equal to 0. So this means that I1 plus I2 plus I3 equals 0. And now we've got convention. So I've got current coming into a node. So that tells me I1 is what we'll usually do. If it's leaving a node, we'll use that as negative. Minus I2 minus I3 equals 0. So if I do the math here and move these over to both sides, that says that I1 is equal to I2 plus I3. Yeah. Add I3 to both sides, add I2 to both sides. This comes from the laws of thermodynamics. Energy can be neither created nor destroyed. I'm pushing current in, it's got to come out. And I can't create energy. It can change forms. I can make heat here by turning voltage and current into power. Basically here the current stays the same, but I lose voltage as I go across it. I'm creating heat. That's what I'm doing. What this amounts to, though, is if you do all this math and you follow it around the same way you did there, for a parallel circuit series, parallel. Oh, and sometimes you'll see this parallel, 2 lines together, or sometimes that to show parallel circuit. So you got 2 parallel resistors, R1 and R2. If you do all this same math against the current law and knowing what the voltage is and everything else, you will get that R total is equal to plus how many of them, ever of them there are. So plus, if there's 400 resistors, we'll go out to R400. If there's 400 resistors, we'll go out to 1 over R400. Important. We won't get into circuit analysis. I'll trying to stay away from analysis. It's easy to fall into the analysis regime where you talk about it and you come back and analyze a circuit and see why it does what it does. I'm trying to stay away from that. So kick me or something if I start to do that. Okay, now we're going to put, batteries. Let's talk about batteries. A battery or a voltage source in series with another voltage source this is V1, V2, and V total here. V total is equal to V1 plus V2. One AA battery is 1.5 volts. Put two of them together so that they're little, that end. That's 1.5 volts. That's 1.5 volts. This is 3 volts. Voltage sources in series add. Voltage sources in parallel do not do this. Voltage sources in parallel get really weird and are potentially dangerous. So I'm going to tell you that don't put your AA's in parallel unless you know what you're doing. So if you do this, if they're both 5 volts, I don't know why I keep putting that hook on there. This is a simplified lie. If they're both the same voltage, you can tie them together. What did I say about an ideal voltage source? 0 resistance. These represent wires. If this is 5 volts, and that's 5.1 volts, that means that I have a difference. Now the truth is there is a resistance in here. And because I do all of this math, I can look at this as being the voltage across the internal resistance there, because I subtract 5 volts from both sides if I do my Kirchhoffs voltage law. And now that means that no matter what my circuit is out here doing whatever in the cloud, all my current's flowing that way through there, generating heat. Eventually something goes boom, if there's enough current. Because those resistances inside of a good power supply are practically a wire. And if I take, let's see, V is equal to IR, resistance is practically 0, so I equals V over R. If that's practically 0, then that's equal to infinity. And P equals I squared R. That just went to infinity squared, and that's not really 0, it's a tiny bit. That's a lot of power in a lot of small space, and it gets really hot and it makes things melt. That's how, like, a hairdryer works. Really low resistance, tied directly across stuff, turns it all to heat. So, don't do that. There's ways that you can do that, but we'll get to that later. There's special components that will let you do that.
You can do that by accident, by throwing batteries in a drawer with a bunch of junk.
You can do something similar to that by having a AA in your pocket with some keys.
Ah, okay.
I've burnt my leg. Yeah, it's hot, it's hot, it's hot. Well, on a cold day, I'm like, man, it feels just, holy
Basic
cow!
resistance, but yeah.
Two quarters of
Quit teaching him how to make an old fuse box work.
And we're talking about the trick with the double A and the gum wrapper to start a fire.
Oh, we used to do,
Steel wool and the 9 volt.
we'd do 2 9-volts.
Yeah.
And we'd use them for hand warmers.
Yeah, we did that
In the wintertime.
We
It
did that in
gets
the
so
Boy
hot.
Scouts.
Yeah. So let's talk about that for a minute. Back when I was a kid, all batteries were lead, either graphite. They're all alkaline. NiCads were fairly new. Alkaline battery is like a lead acid or a graphite, something else. If those things, the worst that'll happen with them is they'll rupture, and for those little ones, and the acid it's a mild acid. It'll make you itch, and if you leave it there for a long time, it will burn you. With a lead acid battery, when you put a lot of current through it, the acid, so we'll talk about a car battery, most lead acid batteries are lead plus very high concentration sulfuric acid, H2, hydrogen, plus SO4 sulfide, with water to help carry with water in them to carry the ions back and forth. The hydrogen comes out of solution and it gives off hydrogen gas. So if you're jumping somebody's car, here's some safety and some tips. If you're jumping a car, here's battery number 1, plus, minus, and here's car number 2 with their battery, plus, minus. Number 1, always connect the positive terminal first, clip directly to the battery, and then clip over here on the frame, because the frame is ground in most modern cars, and negative ground. Positive comes over here to positive on this side, because you're actually trying to put current into the battery. This is one of the few times that you parallel them on purpose. And then you connect the other end of the jumper cable over here. And this is the dead car. And this is the not dead car. And I'm going to throw a quick, if I put that means not in logic. Or bang. So the reason you do this, you start on the dead car, you connect positive first, and then you connect ground, and then you come over here to the live car, positive and then ground. Because that last connection you're making is going to make a spark. If anything's going to spark, it's going to be that one. The dead battery is going to be the one that gives off hydrogen gas because it's charging. So you want that spark the hell away from that battery. When you disconnect it, you do the same thing. You disconnect over here, because if you disconnect this one first, he's been doing stuff, he could be giving off hydrogen. You don't want to spark hydrogen. So you take off the live one first. This guy's been getting all the current. He's the one that's most likely to give off hydrogen. You disconnect everything from this side first, and then just in case you forgot, you disconnect from the ground first. That way you don't make a spark around a cloud of hydrogen. I know somebody that this happened to, battery exploded in his face and blew acid all over his face. He got some nice chemical burns out of it. Don't do that. I'm trying to scare you. Not really, I'm just trying to make you respect it. So we're going to do something here, and this will become a little bit more apparent in the future. Why we're going to do this one is if I have 2 voltage sources, separated by a resistor. Got the same kind of thing. Now this is something that you will sort of do commonly. Ground is also referred to common, so I got to be careful with my terminology. If I've got a 5-volt source here, and I'll use a 1.2 volt source there, and then we'll work this backwards. So let's do Kirchhoffs voltage law. I've got minus 5 plus V sub R plus 1.2 is equal to 0. And right away I know that VR is equal to 5 minus 1.2 volts, right? Quick math. You guys tracking?
Yeah.
Tracking? Or, what is that, 3.8? 3.8 volts. Now, when you do this, remember I talked about you can have infinite current. You want to limit the current. In this case, when you're doing this, R is called a ballast resistor. I don't know where the name ballast comes from, honestly. I wish I could give you that piece of, but, so let's say that we want I to be 25 milliamps. Oh, do I need to go? I need to go through this again, don't I? Because we got some new people. Units of measure. They're French, Greek, Latin. We'd start at base units. So 10 to the 0 equals 1 and ohm. Okay. 10 to the 1. These are all powers of 10. Equals 10 ohms. If you want to get really clever, you can call it, I think, a deca ohm, right? That'd be a deca ohm. I don't know anybody who ever uses that. 10 squared, 100 ohms. 10 cubed is 1,000. Here's where we start to care. 1,000 ohms is equal to 1 kilo ohm equals 1 k ohm. Here, the vernacular is a k ohm. K ohm. Now I'm going to skip. Now we're going to go 10 to the 6th is 1 million. 1 mega ohm. 1 capital M ohm. You'll hear these when you talk about your computer components: kilo ohms, mega, or kilobytes of RAM, megabytes of RAM. A CD can carry 680 megabytes, 680 million bytes. A DVD is like some gigabytes.
5 gigabytes, give or take.
So we go up to the next one. 10 to the 9th is 1,000, 1 million. So 1 billion is 1 giga ohm, regardless of what the professor in Back to the Future says. It's not a giga, it's a giga. 1 giga ohm. 10 to the 12th. Now you're starting to think these are pretty silly numbers because they're so stinking big, but they actually do get used, depending on what you're talking about. So when we start talking about computers, the next one is a giga is a tera, so 1 trillion. 1 terabyte, or 1 T ohm in this case. It's real common. I think the biggest hard drive I've seen now is like 500 terabyte hard drive.
Yeah.
Petabyte drives now.
They're not just one drive though. I think they're an array. But yeah, so the next is 10 to the 15th. She beat me to it. 1 trillion quadrillion. Equals 1. And I've heard it pronounced peta, and mostly I hear it pronounced peta. But I'm honestly not sure which is probably correct. It's probably peta. But so 1 peta. These days you don't usually see 10 to the 18th, which is attobyte, I think, or an atto whatever. But now we go the other way. So we go 10 to the minus 3 is equal to 0.001. And that is and I'm going to intentionally make, even though I write everything else capital letters, this is a milliohm. Power supplies are measured in milliohms, usually. 10 to the minus sixth, 0.00001 micro. Greek letter mu, 10 to the minus ninth is nano, 0.0000001. You see the pattern? Do I have to keep drawing zeros? Nano, lowercase, even though nano ohm, 10 to the minus 12th, millimicro nano pico, pico ohm, and this is a small p as opposed to that capital P up there, 10 to the minus 15th, millimicro nano pico femto, is a lowercase f femto ohm, and 10 to the minus 18th is as far as I'll go. That is an atto, I believe. No, amto? Amto? I think. This is a question mark. I don't remember. It's been a long time since. I used to regularly deal down into femtos. IC design, you're down in the femtos on things. And way up here in the teras also. But so I'll erase that now. So back to this after that diversion. You want your current here, I, to be limited to 25 milliamps. That's 0.025 amps. V equals IR, 3.8 equals 0.025 R. I left my calculator out in the car. If somebody's got a phone and can do that for me, that'd be 8 times 4 is 16, 32, carry 3, 12, 13, 14, 15.
152.
15. Be 1.5 k ohms. No, maybe it would be 150. It would be 152 ohms. Yeah, because that moves forward. Yeah, 152 ohms. So for this all to hold, that means this R is 152 ohms. There's reasons why you do this, and we'll get to those eventually. Now, last week we also talked about AC circuits and DC circuits. So a battery is DC, so I'm going to specifically use this. And if I look at a graph of voltage with respect to time, and my battery's at 1.5 volts. Oh, I was talking about batteries exploding. Lithium ions, when bad things happen to them, they burst into bright white flames. And it's not kidding, you can't put it out with a fire extinguisher. Until it has burnt itself out, it's going to burn. So be careful with lithium ions, especially these little bag cells that are in really cheap components. If you overcharge them bad and then you cause them to rupture, go look on YouTube. People do it on purpose for fun. They stab them with an ice pick while they're super overcharged and they burst into bright white flames. Get your dad to go have fun with you.
That sounds like our next project.
1.5 volts. So a DC circuit, it doesn't matter how long I go, it's going to stay at 1.5 volts. What you'll see with an actual battery is the voltage over time does this. So if I talk about a car battery, which is a 12 volt battery, right? This is your nominal 12, a full charge is about 14, and then it's considered dead around 9 to 10 volts. And we won't talk about energies and those things right now. Those are when you're wanting to get into small things or do things that are going to be powered overnight while you're running around with lights blinking on your head, then you start to care about kilowatt hour or watt hours and amp hours and things like that. Maybe this guy. Often if I'm doing an AC source, I do that. DC equals direct current. AC, alternating current. Alternating current, most generally speaking, is a sinusoidal waveform. You know what a sine wave is? That sound is a sine wave. Looks like this. More specifically what it is if you were to take a wheel and you were to roll that wheel on a flat surface and mark where this spot is in time, every time it moves, what you'll see is this basically comes down and then it goes up, and it slows down and it comes down and it does that. It's a sine wave. I was talking earlier about sine waves adding. It's called constructive and deconstructive interference. Hey.
Hello.
If I have a sine wave and another sine wave that's perfectly the same, you get this whole voltage adding thing. So if they are the same amplitude, is this amplitude and this, think about waves on the ocean, is your wavelength, which is signified by the Greek letter lambda. You have wavelength, you have an amplitude, and you have, it's going in time. So the wavelength and the time are directly related. And in the case of electronics and radio frequencies and things like that, their relationship is the speed of light. In free space, which is a vacuum, and air is really close to free space. On our walls, our wall outlets, this is 120 volts AC, and I'm going to put this over here because nobody ever says it, RMS, root mean squared. What you will see if you put an oscilloscope on that and you don't blow up the house is that this peak here, so when we start talking about when we talk about our AC, you have your peak voltage, which is this voltage. You have your peak-to-peak voltage, which is this voltage. So this is V peak to peak. This is V peak. And you have your V RMS, which generally only works well for sinusoidal waveforms. You can work your way and do the math and get the RMS for square waves, triangle waves, anything else, but it's easiest for this. And we're going to have to get to it here. The 120 volts RMS is what the equivalent DC value of that is. So if I were to have a 120 volt DC source, it would be the equivalent energy, power, whatever you want to put it, coming out of the wall as that 120 volt AC source. It is the square root of the mean. So let's say I break this into 60 pieces, or 100 pieces. Let's say I break it into 100 pieces. The mean of the voltages squared. So V1 plus V2 squared plus V100 squared. The root of the mean of the squares. Root mean squared. Practically speaking, on your wall, the RMS is equal to 120. It's a square root of 2 relationship, which means V peak. This has been so long since I've done this. I don't use AC normally. It's 170 volt. Oh, looky there, I can right up to 60 hertz. And because this is a technician book, I can probably find it right here. I don't want to lie to you and get it wrong. That's phase angles, alternating current. RMS is equal to 0.7 times V peak. So 120 divided by 0.7, I think is 1, does it say right here?
171.
Is it 171? Okay, that's what I was thinking was 170. 170, and that means then the V peak to peak is 340 volts. Is that right? That doesn't seem right. That doesn't seem right, but I guess it is if we got it right. Because there's a square root of 0.7, it's actually 0.707, which is the square root of 2. No.
Square root of 2 over 2.
Yeah, right. Yes. And it's square root of 2 of the whole thing, square root of 2 over 2 of that. Thanks. I don't do AC often.
Last week you said that 120, the 120 in the wall is sometimes referred to as 110. And
Right.
you explained why, but I forget why.
Right. So,
Yeah.
so here's the deal. Outside your house, somewhere, the transformer, you've got your house, and you've got your fuse panel inside, and out here, you've got your power line that comes in. So there's like usually a transformer hanging on the power line. He goes off to some other power lines, and you see them connect in, and they come down to your house, right? At this point, it's supposed to be 120 volts. If you follow the rules and regulations and codes of the National Fire Protection Act, Section 40, I think, which is the National Electric Code, which is written completely. All of our building electric codes are part of the Fire Protection Act, so you don't burn your house down. It says that the maximum length of wiring that you're allowed to do, so, okay, I said wires have 0 resistance. That's not true. They have a little bit of resistance. The bigger the wire, the less the resistance. But the longer it is, the more the resistance. Which is why a small wire, you're only allowed to carry a little bit of current, and a big wire, you're allowed to carry a lot of current. To an outlet here, the maximum voltage drop is 10 volts. So that means that at any outlet under the full load allowed for that size of wire and current, whatever. So if you got a 15 amp breaker, it's got to be at least 14 gauge wire, I think. So at 15 amps and 14 gauge wire, this voltage will not drop below 110 volts. The more things I have out here using power, the more things, the lower, it won't go below 110, but it might not be the full 120. So what that practically means is if you're designing a circuit that has to plug into the wall, it has to be able to accept anywhere between 120 and 110. And then you hear people say, oh, well, you know, but usually it's around 150. It's in the middle, people call it 110 volt, 115 volts. So here's somebody talking about 110, 115, 120 for household voltage. They're talking about the same thing. It could be anywhere from 120 to 110, depending on the load and how close you are to the breaker box. It's sloppy, and you gotta, so when you design a circuit though, you have to take into the two extremes, right? And in a brownout situation, this can drop down to 90 in the worst case. So you really, and then power spikes can bring it up. You usually talk about plus or minus 10%. So you want to be, you know, between 130 and 100 that your system will work, because stuff happens sometimes. Let's see, where was I over there? I was talking about sine waves. Oh, I wanted to introduce the concept of digital and analog, because that kind of flows from the AC and the DC. So if I look at in time, when I'm using microcontrollers and computers and things like that, generally they speak digital language, ones and zeros. We generally, and I'm using big generalizations here because this isn't, I'm lying to you, we use, say, 5 volts and 0 volts. This might be a 1, that might be a 0, that might be a 1 as time goes on, and I might do a 0 and then a 1, 1. And you'll notice that one of the things that becomes completely apparent is if I look at this at any given time, there, I don't know if this is this 0 or that 0. So there has to be a way in your communication of knowing when things start and when things stop, and there is the understood, I'm having a vocabulary failure, the understood concept of a clock, time. When you are running a microcontroller or a computer, you hear about clocks, and clocking, overclocking. What you've got is a special piece of hardware in there, and that supply is actually usually like this. It's a clock, and what it does is it puts out a constant stream that looks something like this, and I've done that really badly. It looks something like this. And when two devices that are some distance apart talk, somehow they supply information about the clock to each other, whether they actually supply the clock or they embed it in the stuff that they're doing, so that you know that whenever this is high, I sample there, sample there. So I know that when this one happens and that one happens and this one happens, I know specifically then which one's which. The truth is we actually sample on the edges usually. So these are offset a little bit, so the edge, try and set the edge up to happen so that the edge happens right here in the middle of that bit time. And then when you start talking about your communications channel, the channel is like a river channel, water information flowing through the channel. You start talking about bits per second, kilobits per second, megabits per second. Back in the really old days that I can remember, and maybe you, an acoustic modem that got 120 baud. So, difference between baud rate and bit rate. If you're using RS-232 serial protocol, as an example, it sets up timing. So it has Always one start bit. And then you can choose 7, 8, or 9, usually data bits. 0, 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7. And again, this is in time going that way, so that actually happened first. And no parity bits is what we usually use. And then one stop bit. And it could be 1, 1.5, or 2, if I remember right. And I think there's some applications that can do 3. And all this stop bit is for is to give it time so that the system knows, oh, those bits there were together. And so inside you run a clock and you say, oh, I'm running at 4800 baud or 9600 baud or whatever the baud rate is. The baud rate is slightly different than the bit rate. So this start bit and stop bit, these are overhead. So for me to send 8 bits down the pipe, I actually had to send 10. My baud rate, if I'm doing 4800 baud, says that I am doing 4800 times 8 bits, small b, of usable data. But my channel is actually 4800 times 10 bits per second. So I'm putting 48,000 bits per second down, but I'm only getting 48 times 8, whatever that is. I can't do that math in my head either. I'm getting less than 48,000 bits per second of data down. That's the difference between baud and bits per second. But we use them interchangeably most of the time because that's less than a 10% overhead. Actually, that's actually a 20% overhead for that one, so it's considerable. But some of the stuff we do now, we're not sending a single bit at a time. We're sending I'm getting ahead, but this is a symbol. And now we get into analog. Analog, if I look at it in time, amplitude, which is height, and the time. Excuse me, I'm sorry, I've got gas tonight. I keep doing it over by you too. At any given time, the voltage can be anything. And so we use something called an analog to digital converter. Sound, for instance. Could be anywhere in there. It's this happening over and over and over. Me talking is this plus that plus this other thing plus this. All these different tones that are being mixed. When I record sound, I'm sampling really fast and building a digital representation of that. And then later I come back through a digital to analog converter to turn it back into the mix of these tones to play over my speakers. It's been an hour. You want me to go a little bit further? Are you guys done for the night?
Yeah, go ahead.
Okay, I really hadn't thought about it. So, on an aside, one of the things that we do with communications channels, if you think about this, right, a cheap analog to digital converter, I mean, honestly, this thing that we call an inverter, or this is the symbol, is a digital logic. It is a sampler that samples this or that. an analog, and it can tell me two states. What we call an analog to digital converter, we won't get into it too much, but our microcontrollers generally have one that's at least 8 bits, which means 256 different states. So it can tell, it can count from 0 to 255 different levels in there. But that's a lie, because usually the bottom 1 or 2 bits are trash. So it's more like 128 or 64 bits of data, 64 levels of data. So I'm rambling back and forth, but let's get back to some, I'm staying away from AC for the most part, but let's talk about a couple of the other basic passive components. And these are, I'll probably stop with these because these take some time to wrap your mind around. So we talked about our various voltage sources, DC, AC, a clock, or a pulse. We've got, so these are sources. Oh, and a current supply. Oh, another symbol for a current supply is this. Usually with an arrow going through. And then passive, I'm going to use passive, I'm going to underline passive. Passive components do nothing but store energy, release stored energy, or convert energy to heat. I think that's true. I don't think I'm telling a lie. So we talked about a resistor. I gotta do this. I gotta do this one good. And you'll see why here in a second. Got a resistor in ohms, and I'm going to do the water analogy over here. To help you wrap your mind around this. So a resistor is a narrow spot in a pipe, right? I've got some pressure, voltage, pushing water through, but it can't get through. So the amount of current going through it goes down. Think about a river. A river that is really wide, but only this deep, has a lot of water flowing through it, has a lot of current, but it doesn't have a lot of pressure. If the water's this deep, but it's only this wide, it's got a lot of pressure, pushing the same amount of current, but through a smaller place. The next thing is a capacitor. I'm going to draw 3 different capacitors. These are all the same. The difference here is they're not the same, that's a lie. A capacitor stores charge. Capacitor, put it over here. Capacitors store charge. This is what we call unpolarized. This one doesn't matter which way you put it in a circuit, it doesn't care. These two are polarized. This is the positive side on both of them. This is the negative side. If you put these in a circuit backwards, they can go boom. and they make a spectacular flash when they go off. And depending on the kind, an aluminum electrolytic, for instance, the electrolyte inside of it is acidic and it will burn you. Not the least of which is because when it comes out, it's usually at about 400 degrees. But
Old boss of mine was repairing a PC power supply, and I hear a loud bang. Look back, I see a fountain of sparks going all over the warehouse ceiling about 20 feet above us, and the smoke from it was being pulled out from the fan in the power supply that was still going, so there was a column of smoke and a column of fire.
I was working on a board once that I built. It was about this big, about a foot by a foot. It was 10 layers. It had about 1,500, 2,000 components on it, mostly analog. And I was reaching across to a power supply when one of them let loose. And I saw the bang and a spark that was about that long shoot up. I could see it on both sides of my arm. And I flipped my chair over, I hit the table. It scared the hell out of me. Capacitors, this is their symbol because what's happening here, some of the physics, is it's literally two plates. And the old Mylar ones, it's two layers of aluminum with a sheet of Mylar in between them, and they roll them up. And you get this really long plate. But what's going on here is when I put a voltage on this material in between, the electrons get drawn to this side, leaving holes on this side, right? So I put this voltage on there, it draws all the stuff over, and when I remove the voltage, they stay over there. Because there's no way for that electron to get back around here, and that potential stays there. You can charge a capacitor, and very good capacitors will hold their charge for years. Years. TV tubes, old tube TVs, the voltage that, I'll use it as an example. It's shaped like this, the tube, and there's a thing here on the back. You've got an electron gun here spewing electrons in, and you've got a big positive voltage here that lets these electrons come back out of the tube and be able to go back into the circuit. Otherwise you wouldn't be able to spew them out into the tube, right? Because you've got to have a return path for the current. It has to be a full circuit. That's general rule of thumb was 1,000 volts per diagonal inch. So if you had a 30-inch TV, you were sticking 30,000 volts back there. And that tube is a damn near perfect capacitor. It will hold its charge for decades. I've seen people get the shit knocked out of them at 5 or 6 years sitting out on a porch. First thing you always do with a TV tube, if you got one, is you ground it out with a couple of screwdrivers that are connected together with jumper clips, because it will kill you. It will kill you. The water analogy of this, okay, well, these two plates are, you know, in a sort of a three-dimensional drawing. Kind of like this, right? So I've got a positive plate, and then, well, if I draw it the way I did over there, a positive plate and a negative plate. The capacitance physically is there's a material in between that has a dielectric constant K, and you have a distance between the two plates D, and then you have an area of the plate that's height times width. And the capacitance is a function of these things. Height times width times dielectric constant divided by the width. So you can make a really big capacitor, big, by pushing the plates really close together, and that's the game, is to get them as close together as you can so that you can get the size down. The water analogy of this thing is actually required by law in Anne Arundel County on new plumbing installations. It is a can with a piece of rubber put across it. So if you can imagine a water balloon is a capacitor. It's a water capacitor. When you fill it up with water, you put pressure on it, right? It blows up. You tie it off and you walk off with it. And that water is under the same pressure it was when you put it in there, right? If I go and pop it next to you, it's going blam! It doesn't just pour on your lap, it blows all over the place, right? That's a capacitor. A water balloon is a capacitor. I don't think I've ever heard that before from anyone else but me, but it's something I was like, oh my God, light bulb moment, right? So I try to, so water, what use is this, right? If I have noise on a signal, because remember, from an electrical, from our maker point of view, I have something over here giving me a voltage, and there's some resistance in the line, and now I have my Whoozy Watts it right here that might be the current going through it is maybe going like this, right? 1 minute I'm using it, I'm transmitting bits down a pipe, right? I need current, I don't need any current. I need current, I don't need any current. I need current, I don't need any current. Well, what that means is, because I do have some resistance in the line, that means my voltage is doing this too. When I don't need current, my voltage comes in here, expands the water balloon out. When I do need current, this thing gives it back to me. When I don't need it, it fills up. When I do need it, it empties out. When I do need it, practical application, that's the thing that capacitors are most widely used for. Most widely. They have another,
So essentially, it just cleans up their voltage signal.
yeah. There's one other thing that they're commonly used for, and unless you recognize what they're doing with it, you don't notice that's what they're doing with it. So if you imagine my water pipe goes into a metal can, and I've got this rubber membrane in it. Now, if I push water in, eventually it's going to stop flowing, right? But while that water's going in, I've got water coming out the other side. But once it stops flowing, it stops flowing. In time, that's my DC signal, right? So if I put DC on this, if I look at this in a circuit this way, I'm running out of board space. DC, what you see, the V1 and V2. I'll mark, this is V1 and V2, okay? What I see is V1 looks like this, V2 looks like that. Because this current comes in, but eventually it can't push anymore. It's done. That's what's effectively going on. Physically, what's actually happened is I've charged my plates up. All the electrons that can move to one side have moved to one side. All the electrons have moved, or all the holes have moved to the other. If I put too much volts on it, I actually cause physical tear. Electrons will start to arc through, it burns, it goes bang. But what it does is it blocks DC. But now if I have a, let's say an AC circuit on here through some sort of a resistor back to ground. Now if I look on the V1 side, I've got this, right? I've got the AC circuit feeding in on top of DC because the voltages are going to add, they're in series. what I'll see on the other side is once this charges up, I took the DC out of it. It lets me isolate DC. That's useful. Because most of the time that we use, this is getting ahead, but in your maker projects, the electret, you usually use an electret microphone is what it's called. The microphone gives you your audio signal writing on a DC. And you've got to get that DC out of there. Depending on what you're doing with it. You've got to get that DC out of there to keep it, to process your signal.
And I guess capacitor is also used for things like flashes where you store a charge and then discharge it very quickly.
Yeah. Yeah.
I think we're gonna probably have to take off.
Okay, I was going to do one more inductor.
One
so
more,
that's
okay,
gonna be
that's good, okay.
Okay. The last one is an inductor, and this is why I got to be clean with my resistors. An inductor looks like this. You can see how you can get it mixed up if you're dirty. An inductor stores current. I'm going to lie and say there's no such thing as a good inductor. If I put a voltage across this and current starts to flow through it and then I short it like that, it will keep that current flowing forever if everything is ideal. That current will be there always. Just like a capacitor will store the voltage forever. Inductors really don't. There's too many losses. The way to think of an inductor is a water wheel. If you imagine this. If I start pushing water through this, at first this thing doesn't move because it's heavy and I don't want to move, right? Inertia. But then it starts to spin. And it finally gets up to the speed where it's spinning at the same rate as the water coming in. And then if I shut the water off, what happens? That thing's still spinning. And it pushes out whatever little current it can, and it actually pulls suction on this side. With an inductor, what's going on is when the current's going through, current in a wire creates a magnetic field. And you have all these wires that are in a loop like this. So you guys will talk about this in physics in 9th or 10th grade, maybe 11th, somewhere around there. Right-hand rule, if current's flowing this direction, my thumb, the magnetic field wraps this way. The magnetic field resists changes in the current. So if I try to push more current through it, that field's got to grow before I can get any more through it. But if I try and take current off, that field starts to collapse. Magnetic field crossing a wire creates current, depending on which way it's going. They wrap them in tight little coils so that they all interlock, and if any one of them starts to fall off, it causes the other one to generate more current. And force of nature. The reason that they don't store current well is because of the resistance in the wires. Resistance in the wires kills it. And with superconductors, you might be able to get there really good, but otherwise. There's a couple useful things you can do with this, and talk about it just a little bit because you guys want to go and it is getting late. A transformer. This represents a core. And this represents polarity. So if I put this here like this, when this goes positive, this goes positive. If I put it down here, when this goes positive, this goes negative. Or this goes positive, positive, positive. If I put my 60 cycles into there, so over there on the wall is my transformer. The practical use of this is as that magnetic field expands, it crosses this set of coils. They create their own voltage. When this one collapses along with it. And so if I've got 120 volts here, if I have, and it's based directly on the number of turns, if I have 1 turn, 10 turns here for every 1 turn there, now I've got 12 volts coming out this side. Yeah, 10 to 1. Trying to make sure it's not the other way around. If I have 10 turns here for every 1 turn there, then I've got 1200 volts coming out this side.
And am I wrong in saying that's how wireless charging works?
Yeah, it's not
Basically.
necessarily this.
Right.
This is an air gap and it's 2 things sitting apart from each
Yeah.
other. But your wireless chargers are basically doing that, and it's wireless chargers are really inefficient.
Oh, yeah.
You're wasting a lot of power because this is awful.
Mm-hmm.
You know, these on real transformers are often iron, laminated iron, and big cores that physically, if you look at them, you've got one coil set up sort of as a cylinder here, and another coil set up sort of as a cylinder here, and then the transformer itself, that core goes through like this because the metal directs the flux, directs the magnetic flux, and keeps it in here. When you've got no air, it just kind of goes everywhere. You can't focus it. It focuses it in. A really good, you know, if I go to some vendors every now and then that have transformers made at my work for what we do. You can get up to 0.99 efficiency, tuned at a specific frequency, at a specific load, but 0.95, 95% efficiency is a good number. 96, 97, somewhere around there is about what you usually see for a good iron core, well made. As soon as you go to air cores, things like that, what you're talking about, they make up for it because they go to a higher frequency, so you get a little bit better, but they're still probably at best 80, I'm guessing 80% efficient.
Mm-hmm.
So they tell you you're saving all this energy with this phone that has a great big battery. You don't have to charge it so often, but you're using a crappy charger with it, so you're not really saving any energy. And I think that's a good place to stop for tonight.
Awesome. Thank you, Tom.
Thank you.
That was very good.
Next time, we'll move away from the passive devices, I think, and start to talk about some semiconductors
Okay.
and so-called active devices, active circuits.
So, how long are we going to have these classes? And then when can we perhaps start getting into
Into the microcontrollers?
Yeah.
The way it feels right now, so we're going to have the class again next week, because the week after that I'm out of town, and then we'll be on a week, and then it's Thanksgiving, and I'll be out of town,
Okay.
and then the week after Thanksgiving we'll probably have class, so that's 1, 2, 3 more classes,
Yeah.
maybe 4, because we'll talk about the things that you'll most commonly see. We'll talk about diodes, we'll talk about LEDs, we'll talk about transistors, speakers, electret microphones, motors, servo motors,
Yeah.
uh,
Stepper motors. We want to do
stepper
more
motors.
sensors.
Some different kinds of sensors. So we'll kind of go in, but
About 4 to 5 classes, and then we get into the shop.
yeah, I think so.
Okay.
And I would suggest for that, you can buy an Arduino for $25.
Okay.
An Arduino Uno, which is a nice simple, it's a board that's about that big. It's got an Atmel, which is now microchip, 18 mega 368p microcontroller on it. It's got up to, I think, 5 analog channels, some pulse width modulation capabilities, 16 or so digital input outputs. For learning and for simple projects, it's a great tool. I'm actually using one at work right now to do some
A lot of
data.
flexibility.
Okay.
And
Amazon, right?
Amazon or somebody like, if you go to SparkFun, they have what's it called, an Arduino's Inventors Kit?
So, yeah, there's
Learning kit?
all kinds of bundles. SparkFun, Adafruit.
Adafruit,
Maker
SparkFun, MakerStore. It's like $100. You get an Arduino, you get a bunch of LEDs, you get some, dang it, servo motors, just a handful of different sensors and things that you can do with it.
Okay.
And I think like a temperature sensor is one of them. And we can, so I'm going to suggest that you find something. The nice thing about the Arduino is, you know, for $100 you've got a whole kit that you can start learning on, and especially if you got somebody to guide you through some of the stuff. And you can download their integrated development environment onto a Windows PC. It's free.
Okay.
It uses GCC, which is GNU C compiler, as a back end. It does some funky stuff on the front end. But as far as learning a programming language for embedded, which is what microcontrollers are, C is the language worldwide.
Right.
It is the number
Yeah,
one.
there's tons and tons of code examples and stuff. out there.
But C is kind of hard to understand too. So I know ANSI C. I can walk you through some of it.
I've done it 30 years ago.
Yeah. A lot of people are using Python. There's like Python for embed. It's, I don't
Yeah,
know
well,
what
there's
it's called.
MicroPython as well.
Yeah,
which is
MicroPython.
MicroPython.
trimmed down. But yeah, I mean, when I was their age, I was taking stuff apart physically, but also the software. So for me, if I had code examples and I could change something, go, oh, well, that broke it, and then I put it back, and then I change something else, and I see something different happen.
Right.
You know, just me taking stuff apart and seeing how it changed things was the best tool. You know,
Yeah, oh, yeah.
I picked up the language or, you know, whatever I was dealing with over time as I saw, oh, I changed this and it does this. So
Well, excellent.
Yeah, so
Excellent.
what I think we'll get into some of the basic components, and we might start. I'd like to go through a basic background of some of the components, and then we can start talking about generic use of a microcontroller. And so as we talk, once we get to a certain point, as we start to talk about a component, we'll start talking about the microcontroller and how it works. So you can have a hands-on example right there and make that component work.
Right.
And
And I think these guys may like that.
yeah, I mean, right now, yeah, this is dry and boring, I get
Yeah,
it.
but you have to get to some of this before you can get to the final.
Right,
stuff.
you have to understand some of the very basic stuff of what
Yeah.
I mean, you don't have to. I know plenty of people who just start throwing stuff together and they get lucky and it works, but they don't understand why it works.
Yeah.
And you're going to have a lot better long-term experience if you understand the why it works that way.
well, and it's less frustrating when it works 8 times out of 10 and you don't know why.
Those 2 times.
Yeah, it's like you get lucky 8 times out of 10, and then those other 2 times you're like, okay, you know.
Yeah, and for most of, you know, again, for a lot of what we do in the maker environment is you're stealing somebody else's stuff. They got it to work, and you're like,
Adapting.
okay, here's somebody who did this really neat thing with blinky things on their head. Well, that works. I'd like to do it over here on my car that's driving along. I'd like to have a police siren going on the car, right? So I can use that, right? So there's a lot of adaptation, and you know, when we get to these things, I don't mind if you steal code from somebody else. I'm not going to grade you, but I want you. What I hope is that you learn and you have a good time learning.
Excellent. All right.
Cool.
Well, thank you so much.
Nice to meet you guys. See you next time.
All right.
All right. So I think next week is the next class.
Okay. Same time?
Yeah,
Thursday?
Thursday at 7. Yeah.
All right. Thank you.
Thank
Very,
you.
very much appreciated.
You're welcome.
All right.
And you were AJ,
Aiden.
and you were
AJ,
Aaron.
Thank you.
All right. See you guys.
Bye.